Hey, I'm Bill Kuzmal. This talk is How Asymmetry Helps Buffer Management, Achieving Optimal Tail Size in Cup Games. So I want to start by telling you about a classic game known as the single processor cup game. The way it works is there are n cups. Each cup is capable of holding an arbitrarily large amount of water, shown here in light gray. And there's two players, a filler and an emptier. In each step of the game, the filler first distributes 1 unit of water among the cups, placing the water however they want. Then the emptier selects just a single cup and removes up to 1 unit of water from just that cup. So whereas the filler gets to distribute water arbitrarily, the emptier has to empty from just a single cup in each step. Now, typically we think of ourselves as being on the side of the emptier, and our goal is to minimize what's known as the backlog, that is the amount of water in the fullest cup. Now, you can also think of this as a very natural scheduling problem. So the cups represent tasks, the water in the cups represents work that needs to be completed on those tasks. The filler is making it so that work arrives over time, and then the emptier is a computer that can make progress on one task per discrete time step. So it has to pick one task to make progress on in each time step. So you can think of this as a scheduling problem, but you can also just abstract it away as a cup game. And so it's this game involving cups, and our goal is to minimize backlog. In fact, often we think about a slightly more general game called the P-processor cup game. And so this models the multiprocessor version of the scheduling problem we just described. So in the P-processor cup game, the filler places not just 1 unit of water into the cup, but P units of water into the cups for some parameter P. The only constraint is that the filler can place at most 1 unit of water into any given cup. And then the emptier selects not one cup, but up to P different cups, removing up to 1 unit of water from each of them. So here you can think of the emptier as representing a computer that has P cores and can run P distinct tasks in each discrete time step. And again, the goal is to minimize backlog. So this is the classic cup game. And the reason that we tend to think of it in terms of cups rather than processors is that it turns out this game shows up all over the place. So as we mentioned, it's useful for processor scheduling. It also shows up in data structure deamortization, in buffer management within network switches, et cetera. And so what we do is we just kind of capture it as this one clean problem that can capture all those settings together. And that's why this is typically referred to as the cup game. Now, the way I'm going to go about this talk is first I want to tell you about kind of what are the state-of-the-art results that are known about the cup game right now. And then I want to tell you about an exciting new direction that we're going on, which is to try to do something even stronger than just bounding backlog. So kind of the first state-of-the-art result you should know about is the best deterministic emptying algorithm, which turns out to be the greedy emptying algorithm. So the greedy emptying algorithm just always empties from the P fullest cups. And a long series of work culminating in showing that the greedy algorithm actually does quite well. It achieves backlog big O of log n, where n is the number of cups, and it actually does that no matter what the parameter P is. And as I mentioned, it's the optimal deterministic emptying algorithm. So this is the best you can do. What's cool though is you can actually do better with a randomized emptying algorithm. So what was shown in more recent work is that by using a randomized version of the greedy algorithm, which I'll tell you a little bit about in a minute, you can actually achieve a much better backlog. You can actually get the backlog all the way down to big O of log P plus log n. So if P is small, then this is a backlog of order log n. And in fact, that also is optimal. So you can't do better than backlog of order log n. By the way, why does randomness help with this problem? Well, it's because we assume that the filler is an oblivious adversary. So the filler can't see what the emptier does in each step. And that means that the randomness has this ability to kind of trick the filler. So the filler doesn't know what's going on in the game. And what's neat is that lets you actually get much, much better backlog than you get from deterministic emptying algorithms. Okay, so It's actually worth spending a moment talking about how this randomized greedy algorithm works, because it's very simple, and it's also going to show up as a side character again later in our talk. So the way the algorithm works is actually the only randomness is at the very beginning of the algorithm. At the beginning of the algorithm, the emptier actually puts random amounts of water between 0 and 1 into each of the cups. So this is a little unintuitive because the emptier's job is to remove water from the cups. But at the beginning of the game, in this algorithm, the emptier kind of artificially places water into the cups for the sake of bookkeeping. These random initial offsets are then going to randomize the emptier's behavior forever in a nice way. Then from then on, what the emptier does is they just follow a greedy algorithm. They always empty from the P fullest cups. There's one kind of very important caveat though, which is actually the emptier will never empty from a cup if it contains less than 1 unit of water. And that's because the emptier doesn't want to ever zero out a cup. If the emptier zeroes out a cup, then they kind of obliterate the effect of the random initial offset that was put in that cup at the starting of the game. So the emptier only wants to take water out in integer amounts. But besides that, you just, the summary of the algorithm is very simple. You put some randomness in at the start, and then you empty greedily. And that's the randomized greedy algorithm. Okay, so what we've done so far is we've introduced the cup games. We've seen kind of the two state-of-the-art algorithms. What's the best deterministic algorithm known? What's the best randomized algorithm known? It turns out there's also a whole bunch of other work on this game, dating back all the way to the late 1960s. There's work on smooth analysis, different adversaries, competitive analysis, resource augmentation, varying resources, etc. And kind of all of this work, one thing that it's shared in common is there's a common goal, which has always been to bound backlog. And that brings me to the focus of this talk. And in particular, the question we're interested in for today is maybe we can try to get an even stronger guarantee. So in addition to bounding backlog, maybe we can also get a really good bound on a quantity that we're going to call the tail size. So the tail size is a kind of interesting quantity. The way we're going to define it in this talk is that it just counts the number of cups that contain 2 or more units of water. So here, for example, the tail size is 3. And of course, we don't have to use the number 2 as our height threshold. We could use any constant bigger than 2. But it turns out all of our algorithms work with 2, and all of the lower bounds work with any constant you would choose. So the tail size is the number of cups with height 2 or more. And what's interesting about tail size is that if you bound backlog, then all you've said is what's the furthest behind any cup is. But you don't know how many cups could possibly be far behind. On the other hand, if you can get a small bound on tail size, then what you're actually saying is that almost none of your cups are behind at all. And so this is kind of intuitively a much stronger guarantee that we're aiming for here. And in fact, we'll even see formally later on that small bounds on tail size essentially immediately imply small bounds on backlog. So that's our question. Can we get a small tail size? And the first thing to notice about this question is that if you're talking about deterministic emptying algorithms, then the answer is a resounding no. So in particular, if your filler is adaptive, or alternatively, if you're using a deterministic emptying algorithm, so the filler knows what you're doing, then the filler can actually easily force a tail size of omega of n. What they do is in the first step, so here let's just focus on the single processor cup game. So we're putting in 1 unit of water at a time. So in the first step, what the filler does is they just put 1 over n units of water into each of the n cups. So they spread a unit of water evenly among the cups. Then in each step, the emptier is going to remove water from 1 cup, and the filler is just going to throw that cup out, forget about it forever, and in the next step, they're going to put 1 unit of water evenly among the remaining cups. So in the second step, it's evenly among n-1 cups, then evenly among n-2 cups, and so on. And what happens is that for any constant c, if you do this for n minus n over c steps, then what you're going to end up with is n over c cups, so theta of n cups, each of which has a partial harmonic series amount of water in it, coming out to roughly natural log of c. So depending on how you parameterize your constant c, you can make theta of n cups have an arbitrarily large constant amount of water. In other words, trying to get good bounds on tail size for a deterministic emptying algorithm is just impossible. On the other hand, it turns out randomized emptying algorithms can actually do much better. So here are the two main theorems of our paper. The first says that there's a randomized emptying algorithm, which I'll show you in a moment, that has a tail size of soft O of p plus log n. So remember, p is the number of processors, n is the number of cups. And it achieves this guarantee for any game of polynomial length. And we also give a matching lower bound saying that actually any randomized algorithm has to allow for a tail size at least soft omega of p plus log n. So this is a tight bound on tail size. And what's remarkable is, especially if p is small, then this tail size is really just log n. And so we're actually giving a pretty strong guarantee here, which is that out of all n cups, the number of them that are going to be at height 2 or larger at any given moment is only going to be order log n. So you have a remarkably small tail size. And it turns out the approach for doing this is to take the randomized greedy algorithm that I told you about earlier in the talk and to add just a little bit of random asymmetry to it in a kind of cool way. So first, let's remember how the randomized greedy algorithm works. The way that the algorithm works is first you put these random initial offsets into the cups, and then you follow kind of just a variant of a natural greedy emptying. Empty greedily unless the cup has less than 1 unit of water, then skip emptying it at all. That was the algorithm we saw earlier that's been used in the past for backlog. And to make this an algorithm that gets good bounds on tail size, we're just going to add a little bit of asymmetry to it. So what we're going to do is at the beginning of the game, we're going to assign each cup I a random priority, so a random real number, p sub I, between 0 and 1. So in this example, the priorities that we picked are 0.9, 0.7, 0.1, etc. And for simplicity, I've rounded them to be kind of multiples of a tenth. So how do we end up using these priorities? Well, what's interesting is we actually almost don't use them at all. So when we're trying to choose which cups to empty out of, if the cups have fills more than 2, then it doesn't matter what their priorities are. We just empty from the fullest cups. And as before, if the cup has fill less than 1, we don't empty out from it at all. The interesting thing is if you have a bunch of cups with fills between 1 and 2. In this case, in some sense, it's not really important what their relative fills are. They all have small fills. And so we use this as an opportunity to use our priorities, to add a little asymmetry into the algorithm. So if we're choosing between cups that have fills between 1 and 2, we actually completely ignore what their fills are. And instead, we just empty out of whichever of the cups has the highest priority. So in that case, that would be this cup, even though it's the emptiest of the cups that have fills between 1 and 2. And again, for simplicity, we're just thinking about the single processor cup game here. So that's our modification of the randomized greedy algorithm. And kind of what's interesting about this is this prioritization is really happening in only one small case, but it ends up having a quite substantial effect nonetheless. So in particular, the main technical lemma that we prove is the following. Say that a cup is high priority if it has a priority at least 0.5. So it's in the upper 50 percentile of priorities. So in this case, there would be these 3 cups have high priorities. The main technical lemma in the paper says that with high probability at any given moment, at most order log n high priority cups are going to have 1 or more units of water in them. So almost all of the high priority cups have very little water in them. And so this ends up being the main technical lemma in the paper. And the proof is kind of this kind of an intricate probabilistic argument that ends up being a lot of fun. And one of the things that's actually interesting about this proof is that even though this notion of high priority versus low priority splits the priorities into just 2 categories, in order to actually prove the lemma, what you end up doing is you split the priorities into much more fine-grained categories, and you compare how those those categories interact over time. So in this short time, in this short talk, we don't really have time to get into how the proof of this lemma works, but we can see how it is that this helps us solve our tail size problem. So how do we go from here to a strong bound on tail size? In particular, this is bounding the number of high priority cups that have one or more units of water, but a priori, it doesn't seem to be saying anything about the low priority cups. So for this, turns out there's a nice little trick. So let's do a proof by a contradiction. Suppose we have a big tail size. Suppose we have a tail size that's more than order log n. We'll call it capital T. So here, for simplicity of illustration, we'll set T to be 3. So we have 3 cups that have heights 2 or more, a tail size of 3. And I'm going to show you how to transform that into a situation where instead you have a bunch of high priority cups that have fills 1 or more. So what the filler can do is the filler can spend the next T steps placing 1 unit of water into each of the cups 1, 2, up through T. So let's suppose, just for argument, that the filler does that. Then what's the emptier going to do during those steps? Well, the emptier is going to focus on the cups that have fills greater than 2, because the emptier is greedy on those cups. And so the emptier is not going to undo any of the cups from 1 through T that we pushed above. We pushed their fills above 1. So now what's our situation? Now we're in a situation where before we had some unknown set of T cups that had fills 2 or larger. And now we have a known set of cups, just namely the cups 1 through T, that are guaranteed to have each have fill at least 1. By the way, this actually works even if these cups were among the cups that contributed to the tail size initially, although you have to be a little careful about it. So we have these T known cups that have fills at least 1, and we can just apply a Chernoff bound to argue that about half of these cups should be high priority. So that means actually we showed that if you can force a large tail size, you can also force there to be a large number of high priority cups that have fills 1 or more. And of course, that contradicts the main technical lemma. And so the result is that this lemma about high priority cups actually immediately implies a strong bound on tail size. And actually, the bound on tail size in turn immediately implies a strong bound on backlog. So we've seen that the number of cups with height at least 2 is at most soft O of P plus log n at any given moment. Well, what if we just think of those cups, that is the water above height 2, as forming its own cup game? At any given moment, the number of cups in that cup game is going to be, well, roughly P plus log n. But we're greedy in that cup game. We always empty from the fullest cups. So the backlog is going to be log of the number of cups, P plus log n. And so you get a backlog of log P plus log n. And so what's neat is from our bound on tail size, you then immediately get a bound on backlog that's also state of the art. And so putting the pieces together, that's kind of the overview of how we get our randomized algorithm. That's how we get our tail size of roughly P plus log n, while also matching the best known bounds on backlog. Okay, so I want to conclude the talk with an open question. And kind of this question is based around an insight, which is that all of the known randomized algorithms for bounding either backlog or tail size have the property that their bounds only hold for a polynomial number of steps. And so a natural question is, well, is it possible to get sublogarithmic bounds for an unending guarantee? That is a guarantee that for a game of arbitrary length, at any given step, you have a high probability guarantee that you have sublogarithmic backlog and sublinear tail size. So there's some progress on this so far. So in particular, in this paper, we make 2 pieces of progress on this. First, we show that if you have a very small amount of resource augmentation, which is to say that the emptier gets to empty out slightly more than the filler puts in each step, then unending guarantees are possible. On the other hand, we show that if you don't have that resource augmentation, then all of the known algorithms that we have, in particular, any algorithm that has the property of being what we call monotone and memoryless, can't give an unending guarantee. So unending guarantees stop being possible in that situation. And what we conjecture, and what would be really cool to see a proof for, is we conjecture that actually no algorithm, no randomized algorithm can give an unending guarantee. And it's it's an interesting question because there's a lot of algorithms you can imagine that aren't monotone and memoryless. And so this is an intriguing question, and I think it also is important for trying to understand the applications of the cup game better. Thank you very much.